Hey, welcome back to Calculus. In this video lecture, we're going to try to finish up our work in section 10.3 on polar coordinates. In the first lecture, video lecture of this section, we got introduced to the polar coordinate system and kind of got used to plotting points, converting points, and just kind of orienting ourselves to these two new measurements, this polar angle and this polar radius. So in this second lecture from 10.3, we're going to work on converting equations, not just points, but equations from Cartesian to polar coordinates and vice versa. We want to look at polar functions, just like in the Cartesian coordinate system where it's kind of traditional to write y as a function of x if you can. In the polar coordinate system, we'll try to understand the polar radius as a function of the polar angle. And then towards the end of the lecture, we'll turn our attention towards a calculus question. Once we understand these polar functions, then we'll start asking ourselves about their rates of change, well, at least tangent slopes in the xy plane, okay? So let's start off by just kind of briefly recalling from the last lecture, and we'll kind of put some formulas back in our head about how to convert between polar and rectangular coordinates. So I've drawn there on your screen a picture of the polar plane and the XY plane superimposed on each other. So remember, we'll always do this in such a way that we put the pole at the origin and the polar axis out the positive x-axis. I've marked a point there, and I've written its coordinates in rectangular and polar coordinates, x, y, and r theta. And let me just kind of complete this picture by drawing in a little triangle. I'll just color right over that hypotenuse. This triangle I'm drawing in red is a right triangle, and its legs have side length x, y, and r. And I'm going to indicate the polar angle theta in there as one of the angles in that triangle. And using the usual trigonometric identities, we did this in the last lecture, that x and y are related to the cosine and sine of theta by those two formulas. That r is the distance in the xy plane. It's the square root of x squared minus y squared. And theta is the inverse tangent of y over x if x isn't 0. And I'm going to put my famous quotation marks around that formula because you have to be a little bit careful with it. If you're using a quadrant 2 or a quadrant 3 angle, your calculator is not going to give you what you want when you use the inverse tangent function. The inverse tangent function will always return a first or fourth quadrant angle. Yeah. So if you have a second or third quadrant angle, you need to manually adjust your calculator's answer by adding pi. Right. So that's what the quotation marks mean. Okay. Let's take a look at an example. The first example I want to do is convert a rectangular equation. I'll emphasize it. It's given by x squared plus y squared equals 1. I want to convert that into polar coordinates. Okay, you probably know what the curve in the xy plane, the equation x squared plus y squared equals 1 looks like. I hope you know what it looks like. And we'll draw it here in a second. But let me show you how you could get a polar description of the same set of points. Basically, the recipe is always the same. When you're converting a rectangular equation to polar, everywhere that you see an x, you're going to replace it with r times the cosine of theta. And everywhere you see a y, you're going to replace it with r times the sine of theta. Oops, excuse me. So having done that, my equation looks like that. And then basically, and this is always easy to say, sometimes hard to do, solve the equation for r. Okay, so in this case, I'm going to square these two terms. Cosine squared, r squared, sine squared. I'm going to factor out an r squared. My goal is to solve this equation for r. Sine squared plus cosine squared is equal to 1 for any value of theta. So my equation just becomes r squared is 1. And if I assume that r is positive, then I can say, well, r is equal to 1. So the polar equation that describes the same curve in the plane that the rectangular equation x squared plus y squared equals 1 describes is just r equals 1. It's a much simpler equation. X squared plus y squared equals 1 is a much more complicated equation than the equation r equals 1. Let's draw the curve and maybe we can see why. You know what the curve looks like. X squared plus y squared equals 1 is the equation of a circle. This is actually clear that this is a circle because it puts no restriction on theta and the radius has to stay equal to 1. Well, staying 1 unit away from the center is the geometric description of a circle. Let me see if I can draw that circle up here. Trying to have it snap to a nice circle. No, I didn't want that. I guess I have to have a nicer circle to begin with. There we go. I'll just put in some axes as close as I can to the middle. This picture doesn't have to be perfect. This is the set of points that are 1 unit away from the origin. And again, the rectangular equation that describes that circle is x squared plus y squared is equal to 1. Its polar equation is r equals 1. And the polar equation is much simpler because, well, that object is round. It's a circle. You can generalize this example if you want. If you take the equation x squared plus y squared is, say, equal to a squared, then I'll leave the algebra to you. But if you do the same things and use the same trigonometric identity, you're going to come down to the equation r equals a. So this thing is a circle, also centered at the pole, centered at the origin, but it's a circle of radius a. All right, so the rectangular equation, x squared plus y squared equals a squared, circle of radius a centered at the pole, centered at 0, 0 in the xy plane. That equation is much simpler in polar coordinates. Circles centered at the origin are easier to describe in polar coordinates because they just have the equation r equals a constant. What's the constant? It's the radius of the circle. Cool. All right, I'm going to switch my screen share over to a different window here. I hope this doesn't make a big delay because I'm going to be doing this for all the functions we've discussed today. So let me kind of explain what's happening in this picture. You're looking at 2 different plots in the same picture, okay? The one on your left, I put the cursor over it, that's the polar plane. You can kind of recognize it from the graph paper from the first lecture. I've just drawn some spokes at equally spaced, or not equally spaced, excuse me, but at the standard angles in trigonometry. So you can see the x-axis is theta equals 0. Just watch the cursor. Blue spoke is theta is pi over 6, pi over 4, pi over 3. The y-axis is pi over 2, and so on. All right, so the standard polar angles, I didn't label them there in this picture, but that's what they are. The picture on the right is a Cartesian picture, but it's not the XY plane, it's the theta. You can only see a T here, but the word theta starts with T, so it's just a shorthand. This is the theta axis. There's the angles, pi over 2, pi, 3 pi over 2. And on this vertical axis, I'm just plotting the polar radius, which in our first example was just r equals 1, or it was the circle of radius 1. So when I start moving this cursor up here, this slider, what I'm doing is changing the angle of theta from 0, it's going to stop at 2 pi. In the polar plane, this blue dot is going to trace out a curve as we change theta. So that blue dot is on the x-axis right now because theta is 0. Okay, theta is 0, corresponds to the positive x-axis. So as I start changing this slider, you're expecting that blue dot to move along a circle. The radius isn't going to change because the radius is constantly 1, but the angles are changing. All right? So watching the blue dot, the angle just got to pi over 6. It just got to pi over 4. It just got to pi over 3. Let me stop right here for a second. The angle got to pi over 2. So that's what this picture is showing you over here, is that as the angle changes from 0 to 2 pi, what's the radius doing? Well, it's just staying equal to 1, all right? So if I continue, the radius just got, or excuse me, the angle just got to pi. Look at the picture on the left and make sure, pause the video for a second and ask yourself, do I understand why the dot is on the negative x-axis when the angle got to pi? All right, it's important. That's getting used to this coordinate system. Okay, continuing along, the angle just got to 3 pi over 2, and it finally got back to 2 pi. 2 pi is the same direction as the angle 0, and we've completed the circle. If we allowed theta to take on more values, say in the positive theta direction, that blue dot would just continue to orbit the circle over and over. So this is kind of how we're going to start getting used to thinking of polar functions. Okay, let's go back and look at a second example. See if I can make this quick. Might be a little delay here when my whiteboard's trying to wake back up. Good. Second example, I want to convert the polar equation x equals 1, or excuse me, the rectangular equation x equals 1 into polar. X equals 1, let's draw the picture first this time. You know what that looks like. X equals 1. It's a very simple equation in rectangular coordinates, just setting one of the coordinates equal to 1. So I'll just scale the picture by drawing, that's a vertical line. Doesn't matter what y is, but every point on that line has the same x coordinate, namely those x coordinates are equal to 1. Okay, so that's the picture of the graph in the Cartesian plane. And now the question is, well, how do we describe that same graph in polar coordinates? All right, well, the recipe is the same. Everywhere you see an x, you put an r cos theta. Everywhere you see a y, you put an r sine theta. But I don't see a y, so there's nowhere to do that. So there you go. And then you want to try to solve that for r. Just like we always solve for y in terms of x, we're going to solve for r in terms of theta. So, okay, r is equal to 1 over the cosine of theta. And you might prefer to write that as r equals the secant of theta. So that's our answer. The vertical line, x equals 1, in polar coordinates is described as r is equal to the secant of theta. And we can kind of think about what theta ranges that would be. What's the theta range on that line? Well, every point on that line is either in the fourth or first quadrant. So if I want to take theta increasing over a non-broken interval, I need to kind of think of theta as starting from minus pi over 2 and then increasing until it gets to pi over 2. You guys remember that the secant function itself is not defined, is not defined at pi over 2 or minus pi over 2 because you'd cause division by 0. So this radius will just keep getting longer and longer as theta approaches those forbidden values. So in each value of theta, how I want you to visualize this, I picked to say theta value, okay, the length of this green line is what I mean by r. It's r of theta. It's the cosine of theta. So you can see in the picture, as theta gets closer to pi over 2, the lengths of those green lines are going to get longer and longer, yeah? And in the extreme, you'd kind of shoot off to infinity because the secant function approaches infinity as its input approaches pi over 2. All right. We'll go back to the Mathematica notebook, but before we do it, let me just say that this also can be kind of generalized. If you want to take, say, an equation like x equals a, some constant value of a, then in polar form, if you go through the same manipulations, then you're going to get that r is equal to a times the secant of theta. So r equals a times the secant of theta is the polar equation for a vertical line. I'm going to leave it to you. I think I'm going to make it part of the activity for this lecture that a horizontal line, y equals a constant, would be given by the polar equation r is equal to a times the cosecant of theta. Excuse me. Okay, so horizontal lines are given by cosecant functions, vertical lines are given by secant functions. I think you'll agree that the rectangular equation for this vertical line is simpler than the polar equation. X equals 1 is a simpler equation than r equals secant theta. And again, that kind of makes sense. Lines are straight. They don't want to be described in polar coordinates. They want to be described rectangularly. Just like circles don't want to be described in rectangular coordinates, they want to be described in polar coordinates. The shape of the curve sometimes is easier to describe in one coordinate system than another. That's why we have more than one coordinate system. Gives us an advantage. All right, let me switch over to Mathematica. The switching is not bad in this direction. And I've got kind of another one of these pictures ready for you. This one is a little bit funnier because of the undefined. So this time I'm starting my slider at minus pi over 2. So you can think, here, let me show you a little piece of it. So this time theta, started at minus pi over 2. So you don't see the blue dot yet because it's way down there. When theta is close to minus pi over 2, the secant function is near negative infinity. So as theta starts getting closer to 0, here it comes, it just got to minus pi over 4. Does it make sense? The blue dot just passed the spoke minus pi over 4. So the radius there would be the cosine of minus pi over 4. It's the length of the segment along that blue spoke. Here you can see the angle. So now in the picture on the right, as the angle approaches 0, the radius is 1. In the picture on your left, we're 1 unit away from the pole at angle 0. So we're pointing out the positive x-axis. The vertical coordinate over here is a 1. The secant of 0 is a 1. So now I'm going to show you as theta goes to pi over 2, the secant function is just going to get bigger and bigger. That blue dot gets further and further from the origin. Theta was pi over 6 right there. There's pi over 4. There's pi over 3, and flies off towards pi over 2. So you can't see the whole curve over here. That's just my a lack of programming skill. But that vertical line, x equals 1, is given by the polar function r equals secant theta. This graph that you're looking at on the right is not the polar plane. The graph in the polar plane is the black vertical line. It's the same as it is in the xy plane. We're not changing the curve. What I'm showing you over here, and in the picture on the right, I like that, in the picture on the right, is how to think in the traditional way of what the radius is in terms of the angle. Okay, good. We'll talk about it online, I hope. Let's switch back. This one's a little slower this direction because my iPad's got to kind of wake up. Cool. Let's try it the other way. This time I'm giving you a polar equation. I don't really need to say that. It doesn't hurt to, but it's clearly a polar equation, right? It's in terms of r and theta. Good. So this time I have some polar equation. I'd like to convert it into rectangular. Right? Let's go over to the Mathematica notebook actually and look at the graph of this first. It's a little greedy, but we'll come back and do our work. So this time I'm going to switch over to Mathematica first. Let me look to see, yeah, this is the right picture. Okay, so I hope you're getting used to this. It's 2 panes, lots of the stuff going on in this picture, but on the polar plane on the left, you're looking at a blue dot, and I'm going to let the angle of that blue dot approach just from 0 to pi this time, okay? So on the picture on the right, I've got a theta axis, and I've marked some usual trig function angles, pi over 6, pi over 4, and so on. And I'm going to be drawing in the right the usual picture of the cosine function. So you're going to be thinking about a wave over there. But in the picture on the left, that cosine of theta is not the vertical coordinate, it's the radius, all right? So the blue dot's distance from the origin is always given by cosine of theta. What spoke I draw the blue dot on depends on theta. Cool. So let's see what happens. Let's slowly let theta go from 0 to say pi over 6. If you're watching on the left, you know I'm going to stop when I get to that blue spoke, the first blue spoke, because that's theta equals pi over 6. I'm going to just pretend like that's good enough. Notice in this picture, the endpoint of the curve is above theta equals pi over 6. So hopefully these two pictures together are kind of starting to make sense what I'm doing. And I don't know what the curve is going to look like. That's why I'm using Mathematica. And I'll actually say right now, before I forget, I'm going to make a teeny little bonus video. I promise I'll make it 5 minutes. This video is going to be kind of long. You might have to pause it a couple times. But I'll make a little bonus video. You can do all these polar plottings in Desmos. Okay, so you can sit at your computer and generate your own pictures and think about this. Okay, now let's let theta say keep going. Theta just got to pi over 4. Keep going. Theta just got to pi over 3. Keep going. Theta just got to pi over 2. Okay, so we're back at the pole because the cosine of pi over 2 is 0. So the radius has just become 0. Okay, it was getting smaller and smaller and smaller. The point was getting closer and closer to the origin. When theta got to pi over 2, the radius became 0. So now this other part, pi over 2 to pi, that's the second quadrant, right? Look at the cursor on the left. I'm moving it around in the second quadrant. Watch, theta is pi over 2 right now. Then it's going to be 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. Okay? But watch where the blue dot goes as we move through those. The blue dot is not moving in the second quadrant. It's moving through the fourth quadrant. What is going on? These theta ranges, pi over 2 to pi, that's second quadrant. But the curve was in the fourth quadrant of the XY plane when we were there. What's going on? Well, it's why I want these side-by-side pictures. Look, in the second quadrant, the radius, cosine theta, is negative, right? The radius has negative values starting at pi over 2. Well, when we have negative radii, we quote unquote go the other way. So let me back up the animation a little bit here and sort of show you, sorry, I backed up too far. Let me stop right there. You can see in the graph over here, theta is 2 pi over 3. Watch the cursor on the left. 2 pi over 3 is this spoke. Why isn't the blue dot on that spoke? Well, because it's exactly the other way, because the radius there is not a positive number. The cosine of 2 pi over 3 is negative 1/2. All right, it's a negative 1/2. Cool. Ignore the, sorry, I'm just noticing this in my video. Ignore because I'm not talking about the cosine, I'm talking about 2 times the cosine. Sorry about that. The label on the, here, I'll fix it while we're talking. Now you know I don't edit these videos. We're looking at r equals 2 times the cosine of theta. So that's why when we got over here, the value of it wasn't negative 1/2, it was negative 1. Okay, sorry about that. But hopefully what I was saying before is kind of helping you understand what this negative radius is doing. So here's the answer to the question. What does r equals 2 times the cosine of theta look like? Well, it looks like a circle, it looks like to me. I don't know if that's a circle. It looks like a circle. It's not centered at the origin. But I wanted to show you this picture in Mathematica so that you can start thinking about what happens in a polar graph when the radius is negative. All right, so let's switch back and do some algebra. Have I warned you a couple times already that this video is going to be a little bit longer? This is the third example of, I think I want to do 5. So if you're feeling tired, take a break and go back and start it back up again. All right, here it comes. I'll stop stuttering. Yeah, good. So we want to do the algebra here. We want to convert the polar equation into rectangular coordinates. So instead of scrolling back up, let me just write down here that when you're doing this, what are our equations? We've got r is equal to that. We've got theta is the inverse tangent of y over x. That's if x isn't 0. We've got that r is equal to, that x is equal to r times the cosine of theta. And we've got y is equal to r times the sine of theta. Okay. So we could start, replacing r with the square root, but let me suggest sort of another way. It's easier to keep using these equations if you can avoid the square root and the arctan. So when I look back at my original equation here, I see a cosine theta. I wish it had an r cosine theta in it, because if it had an r cosine theta in it, I could swap that for x. Okay, I'm trying to convert into rectangular coordinates, so I want the equation to look like x's and y's. So I'm going to do something that maybe will seem a little sneaky, but I'm going to multiply both sides of this equation by r. All right, so I'm just going to take the equation r is 2 cos theta and multiply both sides by r. I get r squared is 2r cos theta. Well, on the right-hand side of that thing, r cos theta is x. That's why I did it. I want to see things like r cos theta and r sine theta if I'm switching to rectangular coordinates, because I swap them for x and y. As a bonus here, on the left-hand side, I got r squared. I know that the square root of x squared plus y squared is r, so r squared is just x squared plus y squared. All right, so in some sense, I'm done right there. That's the equation in x's and y's that has that same curve. It looked like a circle. If you want to try to prove it's a circle, then what we need to do is something called complete the square. All right, so to complete the square, well, let me do a little bit of algebraic prep here for a second. So I take all my x terms on one side. I'm going to leave a little bit of space there. It's already a perfect square in y, so I just subtracted 2x, and then I'm going to add a term to the left-hand side to make that factor as a perfect square, and that term in this case is a 1. In general, what you do is you take the linear coefficient, you take the coefficient of the variable to the first power, that's our -2 in this case, you divide that by 2 and you square that. That's the number that you need to add to make it factor like a perfect square. But since I added 1 to one side of an equation, I have to do it to the other to keep it balanced. And then this thing will factor into x minus 1 squared. Y squared's already factored. And I can see that that's a circle of radius 1, centered at the point 1, 0. And if we flick back to that Mathematica slide, we'll do it in a second. We'll see that, yeah, that's exactly where that circle was centered. Its radius was 1. It was centered on the x-axis at the point 1, 0. Cool. All right. So more generally, all of these will have a more general. If you take an equation that looks like r is equal to a times the cosine of theta, and you want to convert that to rectangular coordinates, you'd have to go through a similar process, and you would complete the square, and you would see that it graphs a circle of radius, well, it's a over 2. It's half that number a, and its center will be at the point a, 0 on the x-axis. Excuse me, a over 2, 0. Okay, talk about it. And your activity, I'm going to ask you something about, let me just write it over here. I'm going to ask you something about r equals a times the sine of theta. Okay. Let's do one more. Just want to continue to talk about those side-by-side pictures in the Mathematica notebook. This is a polar function. If you want, I just kind of made it up. R equals the cosine of 3 theta. And the question I'm writing here, discuss the graph of, if you want a more specific question, what's the graph look like? What does this graph look like? I'm going to try to talk you into answering questions like this using Desmos whenever you can, but I'm going to switch over to Mathematica. I'm going to switch over to Mathematica and try to answer it just by having it draw it for me. Before we do, that circle we were just talking about, look, its center is right here at 1. That was half of our A, and its radius is also 1. All right, so that's if you change the 2 in this equation to some other number A, then the center of that circle is going to be at A over 2, and its radius is going to be at A over 2. Its radius is going to be A over 2. I wrote in the activity, sorry, we have to just kind of scroll through. This is my Mathematica closet. Let me fix something here before your very eyes. So here, I'm not going to say anything about it other than in your activity, I'm going to ask you about something like this, 2 times the sine of theta, not the cosine. And well, I'll just sort of show you the animation real quick. I'm going to let theta go from 0 to 2 pi. And it traces something out. Traces something out. Over here, this looks like a sine wave. Well, because I'm drawing r on the vertical axis and theta on the horizontal axis, so it is a sine wave. It's 2 times the sine of t. It's a wave with amplitude 2 and period 2 pi. But in the polar plane, where r is interpreted as the distance, where theta is the angle, it traced out this thing. And in your activity, I'm going to ask you to tell me what the equation of that thing is, and then tell me what that thing is. Okay? So sorry, a little bit more closet shopping here, but here we have arrived. So in this picture, I have got the equation set up correctly. We were talking about r equals 3 cosine theta, or sorry, cosine 3 theta. And so, well, you know what I'm going to do. These pictures kind of look familiar now. I'm going to start letting theta go through the first half turn, 0 to pi, radians. If you're wondering why pi sometimes, why 2 pi sometimes, it's a good question. We need to settle it, but I'm just going to let theta go from 0 to pi here. And in the picture on the left, at every theta value, the blue dot is on a ray making that angle theta, and its distance to the origin is r, cosine 3 theta. So here we go. Theta is starting to increase. It's climbing, theta is climbing from 0 to pi over 6. In this picture, you can see that as theta goes from 0 to pi over 6, the cosine of 3 theta is getting smaller, right? It started off at 1, it's getting smaller. Well, that's why the blue dot is getting closer to the origin. In the picture on the left, r is the distance. So when theta gets, when r gets to 0, we're at the origin, right? In the picture on the right, I can see that the cosine of 3 times pi over 6 is 0. We just hit the horizontal axis, and that's why we've returned to the origin. The distance is 0. All right, and that was the first pi over 6. So now we're going from pi over 6 to pi over 3. So look at the picture on the left for a second. Pi over 6 to pi over 3 is this wedge where my cursor is, right? I hope, maybe, well, not I hope, but maybe you know the answer to this question already. Why isn't the curve in that wedge? The curve is supposed to be up here because theta is up here. We're between pi over 6 and pi over 3. But the reason the curve isn't is because, pause it, dramatic effect, the radius is negative. When the radius is negative, in the polar plane, you're going, quote unquote, the other way. Okay? So we'll continue here. Now theta is between pi over 3 and pi over 2. Our radius is still negative, so we're not in the corresponding quadrant. Theta just returned to 0. So now it makes sense again, or not, I shouldn't say it makes sense again, but the dot is in the quadrant that corresponds to the angles, right? Between pi over 2 and 2 pi over 3 is this wedge, and the dot is in that wedge. It's because we have a positive radii. All right, so we'll just continue it, making this nice loop. Cool. So the reason I like to have these pictures side by side is that negative radii are kind of confusing. And this picture on the right just helps me see, oh yeah, the radius is negative between pi over 6 and pi over 2, and it's negative between 5 pi over 6 and pi. So over here on this rose, people call it, with 3 petals, you're not going to be in the corresponding quadrants, but rather the opposite ones. Okay, why did theta only go to pi? Because the thing closed up there. If I extended theta, say, to 2 pi, then this blue dot would have just traversed that rose twice. So it ends up closing back up on itself after theta goes from 0 to pi, so we don't need to. Cool. So it's a rose. Nice. Let me switch back. We'll pause while the iPad wakes up. I won't try to draw that picture, but we looked at it with the Mathematica, and it was a rose with 3 petals. A rose with 3 petals. Petal like that, petal like, it's not a bicycle, it's a flower, petals. Okay. So I'm not going to do it in this video. It's kind of long, but maybe in our Zoom meeting, or maybe I'll make another video. I am kind of interested more generally in things that look like a times the cosine of n times theta, or maybe a times the sine of n times theta, where n is some whole number. In fact, you can even make it a positive whole number. So, you know, things like 1, 2, 3, 4, and so on. My example, I chose n to be 3. So if you watch the Desmos video that I'm going to make after this is done on how to plot in the polar plane in Desmos, you can play around with these things. You can pick different values of a and pick different values of n and make some conjectures. If you did that before our next Zoom meeting, it could really enhance the conversation, if you have time. Yeah, everybody's juggling a lot here. Okay, so let me go back up to the top real quick, remind myself, we said we were going to convert some equations. We did that both ways. We've talked about thinking about polar functions, getting used to thinking of the polar radius as a function of the polar angle, okay? So it's a different way to plot. What remains? Tangent slopes. Let's talk about it. Tangent slopes. So I want to talk about, how do you find it? Well, actually, we're just going to use that old parametric idea. If you give me a function, r equals f of theta, and I remember that x and y are given by r times cosine theta and r times sine theta, if I replace r with f of theta in those expressions, yeah, then I find out that x is just f of theta cos theta, and y is just f of theta sine theta. Those are parametric equations. Right? You're not surprised. That's why the parametric equations opened up chapter 10. They're parametric equations. The parameter is theta. All right, so we don't have to reinvent the wheel. We know how to find slopes of curves given parametrically. The slope of a curve given parametrically, you take the derivative of the y function over the derivative of the x function, where the derivative is done with respect to the parameter. No quotient rule, just separately. So let's just walk through this together. Let me maybe make a different color for y. So here's the y function, coloring it over in blue and yellow now, so it kind of makes it green. And how do we compute y prime? Well, I should be looking here. F of theta times sine theta. And it's a product. You have to compute y prime with the product rule. So I'm taking the product of the first factor, f prime, times sine untouched. Then f untouched, derivative of sine is cosine. All right, so that's my y prime. You check the bottom. Same thing, x prime, take derivative of f, cosine untouched. then leave f alone. Derivative of cosine is minus sine. So I changed the plus to a minus. So there's a formula. I don't want to look at these colors when I'm using the formula, so I'm going to get rid of them. That's how you compute the derivative, dy dx, the slope. Let's try it on our friend the rows here. I brought it along. I snipped it out of Mathematica. We don't have to switch back. There's our rows. Let me make this just a teeny bit thinner for a second. Trying to find the slope of the tangent line at pi over 6. We saw in the video at pi over 6 that the point was back at the origin. So that ray through the origin, or its other half, makes a line that makes the angle pi over 6. That is the tangent line. This is tangent to the curve at theta equal pi over 6. So basically what I'm asking above, when I'm asking, well, what is dy dx when theta is pi over 6, I'm asking, what's the slope of this line? What's the slope of that line? All right, well, you maybe wrote them down. I can put them back in view. We have to use these formulas. What do I mean? Well, if r is the cosine of 3 theta, then x is the cosine of 3 theta times the cosine of theta, right? X is r cos theta. Y is the cosine of 3 theta times the sine of theta, because y is r sine theta. Okay, so we just have to differentiate those things with the product rule. Can we try to squeeze it right here? dy dx. Pause the video and do it before me. Compute y prime of theta and x prime of theta before me, and then unpause it and look back. So dy dx, I'm just going to write the product rule without saying it. So I have to take the cosine of 3 theta and take its derivative. So that's minus 3 sine of 3 theta times a sine untouched. I'm not going to simplify this thing. Plus, I put the cosine of 3 theta times the derivative of sine, which is cosine. All right, I'm wasting that formula up there. I'm actually kind of doing this from scratch, but now I have to take the derivative of cosine 3 theta. We already did that. It's minus 3 sine 3 theta, but this time I multiply it by the cosine, and I'm going to subtract the cosine of 3 theta times sine theta. So there's our derivative as a function of theta. So if you want in particular, the derivative when theta is pi over 6, well, you have to evaluate this expression at pi over 6. So this has been a super long video. Let's see, can we hack it? Sine of 3 theta, well, 3 times pi over 6 is pi over 2. The sine of pi over 2 is 1. The sine of pi over 6 itself is a half. I'm just going to do the same thing. Cosine of pi over 2 is 0 times, I don't care. 0 times something is 0. All right, so there's our numerator. In the denominator, we get negative 3 sine of 3 times pi over 6 is 1 times the cosine of pi over 6, that's root 3 over 2, minus the cosine of pi over 2 is 0. All right, so that actually simplifies kind of nicely because the 3's cancel and the 1 cancels and so on and so on. So you just end up getting 1 over the square root of 3. So the slope of this line in this picture is 1 over the square root of 3. And if you wanted the equation of that line, since it goes through the origin, didn't ask this in the stem, but I'll just do it now. That is the tangent line. I colored it blue in the picture. At theta equals pi over 6. So you're getting used to this. I keep describing where I am on a curve in the XY plane in terms of what the parameter equals, because I parameterize the curve. Okay, if you made it through that long video, you're a champion. There's a lot of information there. There's a lot more to practice. Getting used to functions in the polar plane takes some time. You can do it. Watch the video again. If you, I'm going to put up a video about how to plot polar things in Desmos, and then hopefully in some online Zoom meetings we can do a lot more examples where you can interrupt me. You can, or not interrupt me, but you can ask me questions. You can stop me, so I don't just talk like I'm doing right now. Okay, so I hope to see you in a Zoom class, and thank you for listening.